In a previous video, we talked about the fact that magnetic field is caused by a charge. So let's actually get into what is the strength of a magnetic field from a charge. And this gets into the Biot-Savart law. Biot-Savart law rhymes with Leo Bizarre. Biot-Savart. Now there are four forms of it. They all pretty much say the same thing. So let's just start out with the basic, is that the differential, this is obviously calculus based, of the magnetic field is equal to mu naught over 4 pi dq v cross r hat over r squared. So this is the first form of it. Mu sub naught is the permeability of free space. Not to be confused with the permittivity of free space. The sub-zero is the free space part. Permittivity is the epsilon. We will bring mu sub naught and epsilon sub naught into play later on. The other form of it, if you think about what r hat is you just take a vector in the radial direction and divide by the magnitude of r. This also can be written as mu naught over 4 pi dq v cross r over r cubed. And so that's another form of it. The third and fourth form deal with current, so let's go ahead and derive that. I know that current is dq dt, and so dq is equal to I dt. So I can make that substitution there, so I get mu naught over 4 pi I times dt v cross r hat over r cubed. VDT is just, well, how far you've gone. It's your displacement. And so this is mu naught over 4 pi I dl cross r over r cubed. And so the direction is the same as the direction of the current. Current officially is not a vector, so it doesn't have a direction. So we take the direction of the current in terms of this. And so we have mu naught over 4 pi I times dl cross r over r cubed, or mu naught over 4 pi I dl cross r hat over r squared. So we have the four forms of it. If we're dealing with a moving charge, we have this. If we're dealing with a current, we use these. I mean, obviously they are very much related to each other since we derive one from the other. Add a little bit of formality to this right here. V is ds dt or dl dt, dx dt, whatever letter you happen to be using. Apparently I'm using L here. So this is dt times dl dt. And you're left with dl. That's slightly more formal. So let's actually run through a problem. If I have an infinitely long wire with a current flowing to the right, I'm going to establish a convention I, J, and given a right-handed coordinate system, so if I cross in a right-handed coordinate system, I cross J is equal to K. So I cross J is equal to K. K is going out at us. And I want to figure out what is the magnetic field at this point P right here. So the magnetic field at point P. Well, that's going to be equal to mu naught over 4 pi. I'm dealing with a current, I, times dl cross, let's go with r vector over r cubed, and then integral from, well, I don't have a single variable, so I don't want to put limits of integration onto it yet. Remember the formula I told you previously in the previous video was the differential of b, and so that's why the integral is here now, and I don't have the differential part there. So what I'm going to do, as I do with so many of these, is I take a small little segment here, dl. I have some angle. I'll put in my sort of artificial values here. Let's go ahead and make this x is equal to 0. Since I've made that an x-axis, apparently, then dl is equal to dx. R There's my r right there. This is some value of y, or some magnitude of y. And so my radial vector, vector from the differential along my current to the point P, is going to be y I hat plus, oh, I need that distance right there. Wow. Try that again. That is x right there, and this distance here would be y. So my radial vector is, so I'm going to the right and up, so x I hat plus y j hat. R itself is the square root of x squared plus y squared. I'm dealing with a very specific distance, so y is constant. So if we come back over here, we have, pull the constants out, mu naught I over 4 pi times the integral of dx is a differential going that way. So that is just regular dx in the I hat direction. So this becomes dx in the I hat direction cross r, which is x I hat plus y j hat. Yeah, that's the cross, and that is an x, over x squared plus y squared to the 3/2. I know that I cross I is 0, so that sort of drops out. And so this becomes mu naught I over 4 pi. So that's 0. I cross j is k, so I have a k hat here. Integral of y dx over x squared plus y squared to the 3/2. Y is a constant, so it's going to pop out, but we now have a single variable here. So my limits of integration are going from negative infinity to infinity. So I'm left with mu naught I y k hat over 4 pi times the integral negative infinity to infinity dx over x squared plus y squared to the 3/2. We have seen this many times before. Rewrite what we have, mu naught. That integral right there is, well, one that I can look up here. So this becomes mu naught I y over 4 pi k hat times, we have x over y squared square root x squared plus y squared from negative infinity to infinity. And you plug them in. Well, first off, this y squared, one of those is going to cancel out. So I'm left on the outside with mu naught I over 4 pi y k hat times x over the square root of x squared plus y squared. Either way, whether I plug in infinity or negative infinity, this y becomes insignificant. And so what I'm left with is, with plug in infinity, I have huge number over huge number. They're on the same, they're both x's once I take the square root of it, because the y squared goes away or becomes insignificant. And so we end up with 1. Stick in the negative infinity. This denominator is positive, the numerator becomes negative. And so in essence, this right here becomes 1 minus negative 1. And so now I'm left with mu naught I k hat times 2 over 4 pi y, or mu naught I over 2 pi y k hat. Making it slightly more universal here, if I have some infinite wire and I have a point a distance r away, this becomes mu naught I over 2 pi r k hat. And you can, again, like with electricity, you can think through what the direction is. Please note that I had current flowing off to the right. So the magnetic field should be coming up out of the page on this side, down into the page on that side, but I was up on the page in the previous diagram, and so that is indeed the k hat direction. And as a reminder, in case you don't want to rewind, I had current going off to the right, k hat coming out of the page. So we did something right. I also want to point out that right there, that is the circumference of a circle that happens to be centered at the wire and going around like that. That will become critical a little bit later on. But this is one of those formulas that we derived and you should know. And this is where we'll do a pseudo derivation to get into what is known as Ampere's law. If I have a circle here, a wire that's in a circle, and this is in radius of big R right here. I have a current that I'm going to have flow counterclockwise. And let's set up our coordinate system, I hat, j hat, and then k hat coming out of the page, because I cross j is k. I'm going to take some differential here. So I have my dl going like that. It's in the direction of current. R, well, let's go back to Biot of R, is mu naught I over 4 pi times the integral of dl cross r over r cubed. R is a radial vector from my differential to the point in question. I'm trying to find the magnetic field at the center here. And so R is a vector like that. So dl cross r, well, dl and r are perpendicular to each other. So mu naught I over 4 pi. So that just becomes r dl. Because they are perpendicular to each other, it is just the product of the magnitudes over r cubed. Now the direction, I have dl going that way, so that's my dl in that direction. My r is in that direction, so dl cross r, because that's the order, is up. So that would be the k direction. R over r cubed is 1 over r squared. R is a constant here, so this becomes mu naught I over 4 pi big R squared, k hat, integral of dl. I'm integrating dl, so that would just be the length. That would be the length all the way around. So this right here is the circumference there, 2 pi r. So I'm left with mu naught I over 4 pi r squared k hat times 2 pi r. Now we have some nice little canceling going on. Pi cancels out, that r cancels out with one of those, and that 2 cancels out with that, leaving a 2. And so I am left with mu naught I over 2r. Happens to be in the k direction. So if I think about that, I've got this current flowing around like that. This is another right-hand rule. Let's actually go through the right-hand rule just to make sure that this makes sense, and then we'll talk about the shortcut that I was about to show you then. So if I have a circle of wire here and I have current flowing counterclockwise, so at this point right here, I put my thumb in the direction of the current, my fingers curl in the direction of the magnetic field. So my magnetic field is into the paper on the outside and coming out on the inside. When I'm over here, my current is flowing in that direction, so I put my thumb in the direction of the current flow. It's going into the page on the outside. And out of the page on the inside. Matter of fact, all the way around, we keep getting this reinforcement that the magnetic field should be coming out of the page inside the loop and into the page on the outside of the loop. This leads into a variation of that right-hand rule. If I just, for a loop, if I just curl my fingers in the direction of the current, my thumb points in the direction of the magnetic field on the inside, which again is out. But again, we said that k hat, it was in the k hat direction, the k hat direction is out, so something went right. Do want to point out that in comparison to something you potentially saw in the other video, that for a circle of wire, we have 2r in the denominator, compared to if I had a long straight wire, I have 2 pi r in the denominator. So just please be careful with that. The number of students have looked at that and go, circle, 2 pi r. Oh, that's the circumference. This is for the circle. No, it's not. This is for the long straight wire. The circle comes from the circle of uniform magnetic field strength. And this 2r, the pi gets washed out.